Good morning, everyone. Welcome to our webinar today. And today's webinar has two sessions. First session is the presentations for approximately 40 minutes, 45 minutes. And then we want to have the Q&A session for the 15 minutes. So let me introduce today's the speaker, Dr. Johnson. I'm really actually excited to have him today's webinar. He is the assistant professor in the civil and environmental engineering at the University of Utah. And he joined the University of Utah last fall. And before that, he was a research scientist and a postdoc at the Alabama Water Institute at the University of Alabama. And he made a lot of achievements and with his colleagues. One of his contributions is the $360 million award funded by the NOAA to improve the hydrological data and the predictions. It was really great. And he received his PhD in the civil and environmental engineering from the University of Utah. His research focused on the advanced machine learning models and the data-driven models to better manage the water systems, especially for the Salt Lake City in the Utah state. I spent my postdoc years with him at the University of Utah, and I remember he was always passionate in about coding, in the machine learning coding, the Python and the R, and especially midnight. And currently, his research focuses on the machine learning and the AI and the sensor applications in the hydrology to improve his water system predictions and disease making and the water demand management, especially in the Western US. And also he has contributed to the training the next generation of scientists and the public and the K-12 the student. So through the workshops with NOAA and the NASA and also the open source software he has developed so far. So I believe he will provide many insights and the future agenda related to the AI applications for water, and the civil engineering, and the environmental management today. So thanks, Dr. Johnson, again for accepting the webinar, the invitation, and then thank you for sharing your research. So Dr. Johnson, over to you.
Awesome, thanks, Singming. One of the fun, when I started my PhD and Singming was a postdoc, one of the most memorable components is when we started a hydroinformatics class.
Oh, yeah.
And I couldn't even load an Excel file into Python. And ever since then, I was very passionate about Python and what data processing and data can do. So for all the graduate students out there or undergrads who are maybe intimidated by the data-driven sciences, I started with zero. And you put the hard effort in and you can work your way up. With that, I'll go ahead and share my screen here. Let's see, hopefully I share the right one. Okay, it's gonna be this one. And all right, everyone seeing? Yeah, everyone should be seeing the screen. Perfect. All right. All right. Thanks. Yeah, thanks for the great introduction. I'm excited to be here today. And we're going to be talking about using large domain data sets, remote sensing products, and in situ observations with machine learning to create high resolution snow maps. And here's just a picture of me. I'm a big skier, skiing with my dog. And this is just up the street from my house out here at Utah in the Wasatch Mountains. All this research is made possible from NOAA, University of Utah, Cairo, which we'll talk about a little bit, the NOAA Office of Water Prediction, and then the Colorado School of Mines. A quick overview of what we're going to talk about today. Water prediction, so why it's important. And then with that, why modeling snow. We're going to go over some of the snow modeling challenges. And then we're getting to the machine learning in snow, specifically focused on the work that my research team has done. We're going to look at the results of the modeling work and like what can we learn? How do we look at the results to see where we need to make improvements? And then just kind of go over the next steps where I see as my personal for our personal modeling workflows, and then as a community. So water prediction, you saw on that first slide that we had NOAA was on it, Office of Water Prediction. So a lot of this research has been stimulated by the recent kind of push for operational hydrology. And much of that is with the NOAA National Water Model. So just a really quick overview of why we're modeling what we want to model is, we're looking to model stream flow. And so stream flow basically in the entire Western US, a lot of that's driven by snow. So we have our hydrological cycle, and what the National Water Model does is creates high resolution streamflow estimation, and that's all about improving our flood prediction, drought predictions, and we have thousands of river monitoring stations throughout the U.S., but they're always at points. So there's a lot of locations, you can think here in the Great Basin, where we do not have a bunch of observations. And so the National Water Model is all designed to kind of fill these gaps. So it has hydrological process representation within the model workflow. And one of those key components for us is that snow water equivalent. So it basically works, it takes in precipitation products from the National Weather Service. But then from there, we're taking that precipitation when it hits the landscape, whether it's liquid or frozen precip, how it translates into soil moisture that leads into maybe surface runoff, and ultimately generate stream flow. And so we're trying to do a prediction service here. And so we want to know that it provides that short range, so near term up to 18 hours. You can think about some of the hurricanes that have hit the East Coast last year. That's about that flood forecast. They want to put precipitation in the right spot so that we can have a flood forecast for how much water is going to be coming down in those mountainous areas. A medium range, so we have some decision lead time up to 10 days. And then they have a long range product that is out to 30 days. And so that comes into that water supply forecasting realm. And that's where a lot of the focus of my modeling snowpack really comes into play. And so by advancing these different processes, improving our data sources, we're looking at advancing water prediction so we can help with emergency management, so like that flood component, and then decision making if we want to have, should we release water out of the reservoirs to make room for an incoming snowmelt? And then a quick blip about Cairo. So that's the Cooperative Institute to Research Operations in Hydrology. This was part of that $360 million grant that I helped write. It has, I think, about 20 different members and partners from different universities throughout the United States. And it's all targeting improving the national water model. So there's 3.2 million miles of stream flow within the model. It includes Alaska, CONUS, and Hawaii and Puerto Rico. And it's all about supporting water management. And then they have this new, it's called the Next Generation Modeling Framework. And this is where different people and research groups can become contributors. This framework is model agnostic. So you can develop certain modules that go in and to help different process representations in the hydrological cycle. It supports interoperability. So there's these standards, so you can kind of plug and play different modules. It's going to be data centric. And so it does data assimilation of different measurements, specifically usually stream flow. For the National Weather Information System, it uses these large data sets such as camels and help to train and calibrate models. And then the biggest thing is it's community driven. So a lot of it's open source software, and it encourages the community to help advance the hydrological field. And then what I'm looking at is improving and characterizing snowpack so we can enhance water supply forecast. And so that's going to support hydropower, ecosystem management, recreation, and water demand management decisions. All right, so we see that modeling water is important. There's a demand for it from the federal government, but what is economic power of water in the West? I like to try to create a story of why would we want to spend millions of dollars, $360 million to improve water supply estimation. And so did a little background. This is very, very high level overview of kind of some of the value of water in the West. And so agriculture relies upon irrigation from snowmelt driven resources. So we have basically winter storms are dropping or precipitating over the mountainous areas that results in snow. and that snow will melt and fill reservoirs. Much of the western US is arid, and there is little to no measurable precipitation during the summer months, which is which is the growing season. And so that's a huge industry, and so we want to characterize snow and then the stream flow so we can better manage our crops. And California in 2023, that was $40 billion came from agriculture that is supported by precipitation and water from the Sierra Nevada mountains. Water supply. So millions of people depend on snowmelt for their water supply in the West, and much of the water supply is not coming locally. So here's just another example of California, where we have all the snow falls in the mountains here in the Sierra Nevada. And all these blue lines are going to be where water is being transferred to. The biggest energy consumer in California is moving water, basically moving water from the mountains up here in Northern California to Southern California. And then we also have the Colorado River Aqueduct. So that's taking water from the Colorado Rockies and the upper Colorado region and brings it into the California where it's a desert and there's not a whole lot of water. Hydropower. So we store water behind dams, and that supports renewable hydropower generation. There's a lot of controversy about the dams, and that's for another topic. But just highlighting, what the hydropower does. So just in the Columbia River, there was 108 billion kilowatts of power generated. And if we assume, basically that could be about $1 billion worth of revenue, and that powered 9 million homes a year is what it can do. That dollar amount I put right there is just based off of general energy prices. It's very difficult to find how much water or how much money that water actually makes, because a lot of time there's different credits in the way that energy is traded nationally. And then recreation. So winter snow activities are a huge driver of economic income. So Vail, one of the largest ski resort companies, generated $2.9 billion last year. And so that's property that is supported by snow, like on their snow resorts, restaurants. So it's a huge industry that snow helps support. And then we have reservoirs, people like going boating, people like going swimming. There's a lot of economic stimulus generated by water from these snowmelt-driven catchments. So we see that water is very strong driver of the economy in the Western US. A lot of that's driven by snowmelt. So that kind of creates a reason to start to understand the water cycle and how we can continue to enhance our economic viability in the Western US. And so what we see is we have a lot high variability in year-to-year flows. So the image I have right here is from the unregulated inflow from Lake Powell. And so unregulated inflow means like what is the natural amount of water that should be flowing from the mountainous areas if there is no upstream withdrawals or diversions. So basically, what would that naturalized system be as far as stream flow? And we see a lot of variability coming in to Lake Powell. And Lake Powell is kind of that division between the lower Colorado Basin and then the upper Colorado River Basin. And so that average is 10.83 million acre feet. But we see there's some really big years that have a lot of stream flow coming into the reservoir. And there's a lot of years that have very low stream flow. And so that variability is what we're trying to understand. And a lot of that's driven by snowpack. That's going to help reservoir operations. That's going to drive water use. Water rights are very important here in the Western US. And there's a bunch of different tiers of water rights. And so if we can better understand what that stream flow variability is going to be, it'll help guide and fulfill those water rights. And so snow is a strong driver of that stream flow. And we also see it has a lot of variability. So this is up at Alta, just down the street from my house in Utah. And we see that there's some years that get 900 inches of snow. Some years are getting down just below 400 inches. And so that is a total amount of snow that's fallen during their season, beginning in October. And we've got to try to better understand and model that. There's a term called peak SWE, melt timing, and this is all affected by the climate. So we'll do a quick look at what that variability will look like from year to year. So here we have the USDA SNOWTEL site, which I'll kind of go over what SNOWTEL is here in a second. And the top right here, these peaks, that is how much snow fell during a specific year. Or the black line, what kind of that average or median is over their historical record. And these peaks are different. So we see, during a low year, during this 2012 timeframe, that peak snow was about 12 and a half inches, and that occurred basically kind of in the middle of March. And then we had, for I think this 2023, which was a very big snow year, we had the peak, which was almost double that value, close to 22 inches, and that occurred in that middle of April. And we have this seasonal long-term SWE graph, and we see a typical peak SWE occurs, maybe the beginning of May, late April. And then we have this strong decrease in snow, and this is when we call melt. And so this is when the snow is melting, and then the amount of water stored as frozen snow in the mountains quickly is decreasing. So these are all components that are important to understand and put to help predict how much stream flow will be filling our rivers, and then we can guide reservoir operations and management. And so you see that term SWE. So that stands for snow water equivalent, and how we measure snow stored in the mountains. So when it typically snows, let's say we have 10 inches of snow comes from a storm, and here we're showing there's only 20% liquid equivalent in this amount of snow. And so that means that maybe only 2 inches of that water is going to, is actual water if we melted that entire piece of snowpack. And a 20% liquid equivalent is a pretty dense snowpack, something we would expect maybe in a maritime snow climate, which would be like in the Cascades and the Sierra Nevada mountains. Here in Utah, we generally have about a 10% liquid equivalent. And if we move to the Rockies, in Colorado, there's a lot less moisture in that snow, and we be between that 5 to 10% component. And so here's a recent paper by Hogan and Lundquist, and just showing that strength of the relationship between the amount of snow or peak SWE that we have in April 1st, and then resulting in that water supply, how much water is flowing down the river. But we see that an important component is we see that it's not a direct linear relationship. There's a lot of variability that goes around their increase or the relationship they're showing right here. So generally, we see the increase in snow water equivalent leads to an increase in annual stream flow, but we're seeing you could have a lot of snow, but not get as much stream flow. You could have a lot of snow and a lot of stream flow. So we're trying to reduce that uncertainty in our estimate, and I feel that by improving our snow estimates in the catchments, we're going to improve how much stream flow we have to support water management. All right, so let's just go a little bit over. I don't know, I'm assuming just a basic level of understanding the hydrological cycle out here in the Western US. And so snowmelt does provide the majority of that water we just saw in that last figure. But let's go over how it occurs. So winter, we get snow accumulation at high elevations. And so this is really between maybe October 1st, and it goes through about April. And it's at different elevations, it will be different. But kind of this general understanding is we have shorter days. So daylight is shorter. That's going to be less direct solar energy is what kind of drives snow accumulation and melt. Cold temperatures, and we have short days. They also have long nights. So everything stays very cold at these high elevations. And our snowpack can be several feet thick once we get into that April timeframe. I think last year we had upwards of like 20 or 30 feet of snow here in Utah during these big snow years we've had the last couple of years. And then late spring, so we're kind of getting close to that point. So that's that mid-April basically time frame. We have these longer days. We have a lot of sun with more direct solar radiation. We have warmer temperatures that are also with that. And so we're seeing a lot of snow melt start to happen during this time frame. And then we get to that summer, we have the meltwater from the snowpack. It's increasing the soil moisture levels. That soil moisture is fully saturated. We're going to be filling our groundwater reservoirs, and we're going to be rising our stream level. So we're seeing a very strong push on our stream flow, and that's going to go downstream and fill up our storage reservoirs. And so we can kind of go over that kind of snow time series I just showed. just to kind of build that understanding a little stronger here. So we have October 1st. So it looks like for the site in Colorado, we're kind of starting that snowpack generally around October 15th. So that's where we've had a couple of storms come through, and we're starting to increase snow. It's cold, has long nights, not a lot of solar radiation, and we're really seeing that snow start to stick and start to accumulate over time. And it does this throughout the whole season until about that April timeframe. And that's when we have that peak sweep. And now we have, these longer days start to hit, more solar radiation, warm temperatures, and that's where we see this really strong snowmelt period. These other little bumps we might see in here, those are just called, maybe we got a storm that came through, a late season storm. It dropped a little bit of snow. It reset that melt cycle momentarily. And then by the time we're in summer, it's hot, it's warm, there's a lot of sun. That snow melt happens very quickly. And then so the majority of that Western US, that snowmelt composes the majority of that annual water budget. So here's just a bunch of kind of local rivers in my area. And so we see, April, we start, when that melt starts to happen. So we have the lower elevation melt, typically happens first, and that high elevation reservoir where the most snow is, we really see that be that pulse of snow melt that drives our hydrographs and our rivers. All right, so we know that snow is important. We see its contribution to stream flow. So what kind of monitoring is done? What kind of efforts done to kind of characterize the snowpack? And so there's two main components of monitoring the snowpack, and one of them is going to be the Airborne Snow Observatory. And so what this is, they have LiDAR they put on a plane, and they're flying different catchments. They do it first when there's no snow on the ground. So you kind of have a bare earth, no snow, digital elevation model. And then they're going to fly over the catchments when there is snow. And so that LiDAR picks up that surface elevation of the snow, and you can subtract that by your digital elevation model of the bare earth, and that's going to give you a vertical amount of snow on the ground. And so that's kind of viewed as the latest and greatest way to spatially measure snow. Um, it's very expensive. And so Colorado and California could spend upwards of $35 million a year to try to characterize the snowpack. And each flight ranges between about $100,000 to $250,000. So it's a very expensive way to monitor snow. SNOTEL, so that's a snow telemetry by the Natural Resource Conservation Service. They're spending about $9 million a year to monitor snow. And so this is temporally continuous. So it's like a site station we're seeing right here. This is a station in Alaska. And so it's every 15 minutes, it's creating these observations. It'll aggregate those to an hourly temporal resolution. And it's been a very valuable resource for monitoring snow in the United States. There's about, I think, 800 to 1,000 of these stations throughout the Western United States and then Alaska. A challenge, though, it's only 1 point, so you don't have a spatial representation of catchment snowpack. Just go over some of the instrumentation that's on these guys. We have air temperature sensors, soil moisture sensors, a snow depth sensor. So this is going to be ultrasonic. So it's measuring that distance from where the sensor is at down to the ground. And then they have what's called a snow pillow, which is measuring that weight of the snow essentially. And so that's how they determine the snow water equivalent. They have that weight and they have a depth that can determine how much liquid content of water is in that column of snow. We also have a precipitation gauge, because even though we're interested in measuring snow, we do get rain on snow events. And so we want to know how much, if it rains, how much rain happened. And then there's just the instrumentation to power it. So there's the solar panel supposed to go and charge the batteries. And we also have antennas so we can send that information in near real time to the data collection centers. And so here's some of the limitations with those in situ observations. So here's Salt Lake City in Utah. University of Utah is right about here. And then we have about 30 different SNOTEL observation sites. And these are just point observations. So this is what the snow is for about maybe 9 square feet of area in these mountain catchments. And they're taking that information and then generating some snow maps or some mapping products that are saying how much that catchment has as far as snow. And the problem with this is that snow is not in its entire catchment. So here we have the Great Salt Lake. This is all for last year around peak ski. And so a lot of these catchments are snow free. There's only snow at certain high elevation areas. And then when we break down what that snowtail observation is as far as the catchment areas, it's not a one-to-one relationship. So if we have 50 inches of SWE at a certain point up in the Cottonwood Canyons, right around here, that's not going to be a full representation of how much snow is in a particular catchment. It's only at that certain point. And so we need a better way to have some kind of estimation of snow. And so we have our snowtail, which is temporally continuous, but spatially discontinuous and location biases. And then we have our airborne snow observatory products, which are spatially continuous, but they're temporally discontinuous and they're very expensive. And so this leads us, well, we need to have a model so we can better understand and characterize how much snow is up in these catchments. So this brings us to some snow modeling challenges. Snow does not fall evenly. It does not share the same processes over different spatial areas. It leads to a very heterogeneous snow distribution. So here we have Little Cottonwood Canyon, just east of Salt Lake City. We get a lot of water from Little Cottonwood Canyon. And this is in maybe like a December timeframe. So there's 6 feet of snow probably on this north-facing slope. This is where all the ski resorts are. And then on this north-facing slope, we have very little snow. It's basically just bare earth. And so there's significant drivers that lead to this heterogeneous snow distribution. So one of them is going to be precipitation. And so we have what phase is there? Is it snow, sleet, graupel, rain? What's the intensity? And that all leads to a seasonal accumulation. And so if it's falling as snow, it'll accumulate. If it falls at rain, it'll just go into either soil moisture or lead to surface water runoff into our rivers. Temperature, and so that affects the density of the snow. So we talked about that snow water equivalent, 20%, 5%, 10%. A lot of that's going to be due to temperature. That's going to drive rain versus snow, and it's also going to be a driver of snow melt. Wind. Wind is a big driver of where the snow ends up. So here we have an image of wind coming from this direction, and we see on this mountain, a lot of that windward side is just bare rock. And then we see on the leeward side, all that snow and it still falls to the surface, and it's collecting on the leeward side of this mountain. So if we imagine this as a continental divide, we need to make sure we're taking snow from this catchment and putting it into this catchment. So that makes it very difficult as far as, where do we put the snow? How much do we put in certain places? Snow can be very light and easy to blow during certain conditions, but, especially after a fresh snow. But during the spring, snow it melts and freezes, and it becomes much more difficult to transport. Creates a significant challenge for putting snow in the correct spots. And then lastly, or not lastly, one of the components is we have elevation. And so we generally see increase in precipitation with elevation. There's a challenge, as we just saw, with getting that high elevation snow. It's very impacted by the environment, by wind, by sun. There's nothing to kind of hold it in place. But this lapse rate, we basically have temperatures cooling as elevation is going to be increasing. We also have windward sides of the mountain and leeward. So generally leeward gets less precipitation, but then you can also have the impacts of wind redistribution. So there's a lot of challenges in modeling the snow just from these couple inputs right here. And so also within the snow modeling world is we have energy. And so energy is one of the strongest drivers of snow melt and snow accumulation. And so one of these is going to be the aspect. And so it's like north, south, east, west. And so this affects the incoming solar radiation on the northern slopes. In the northern hemisphere, we have a lot less energy hitting those slopes. On the southern slopes, there's a lot more energy hitting them, and solar shortwave radiation is one of the strongest drivers of snowmelt. And so if we have less energy hitting those northern slopes, that leads to accumulation. If we have a lot more energy on the southern slopes, leads to a lot of snow melt during the snow accumulation season. Similar if we have east versus west. So it's typically colder in the morning. The sun rises in the east, so those eastern slopes don't get as much warmth with that solar radiation. Whereas on the western slopes, we're going to get more solar radiation with that warm temperature, which can lead to a different change in the snowpack and more melt. We have seasonality. And so seasonality is going to be a strong driver of that solar angle. So it drives the solar inclination, affects the radiation, affects the temperature. Then we're going to have complex topography. So you have rain shadows and then vegetation that are going to be different within the mountainous regions. And so we can just take this is from one of my ski tours, just to kind of give an example, like how can we take this image of the mountains and translate it into some information based on maybe the solar radiation, snow redistribution. So in this image, I'm taking this from north to south. So I'm located kind of right in here. We have Snowbird Ski Resort a little bit to the east of me. This is called Scotty's Bowl. And then we have this drainage that I'm skiing for this certain day. So I'm on this west-facing slope. We can even see in these trees right here on that eastern side of the trees, there is still snow. So it's after a recent storm. That snow hasn't melted yet. On the western side of all these trees, that snow has already melted. So that's kind of demonstrating that difference in energy. So we're looking to the south. So we have this bowl right in here, which is going to be this bowl off of Red Top. That's in the shadow. So this is gonna looks like an afternoon ski tour I was on. That sun is not hitting those parts of the mountain. So that snowpack is staying cold and it's not melting. We have these western aspects. So right here, we're looking up on this mountain peak of Red Top, all of this whole area. That's facing west, so there'll be a little bit of south in there. It's very easy to see how much solar radiation is hitting that part of the catchment. We also see looks like a bunch of snow in this area, and that's likely caused by wind redistribution coming from the south, which our storms often come from, and really distributing that snow from the other side of the ridge into this part of the catchment. And then the kind of final takeaway I want to share right here is that all this area over here is in the shadow. So we have the sun coming from kind of over here, coming from probably that southwestern part. And all this area is staying cold and it's not having any snow melt. So that's a kind of example of how to look at the terrain in an image and seeing how that is affecting these snow processes. And we can take that to that image we looked at earlier. So this whole part of Little Cottonwood Canyon, here we have Snowbird. Snowbird's right here. This is all south facing. And we have a lot of that north facing terrain we're looking at right in here. So we can visually see how that snow melt has led to a lot of snow, been a lot of snow melt. There's just no snow in that south facing catchment. Some other examples we have down in southern Utah. We see how there's no snow at all in the southern facing catchment. We see on the mountains in the south, there's no snow. We have snow on our north faces right here and this part of the image. And then this leads to a lot of different vegetation. South slopes usually have much less vegetation or it's more like shrubby, where our north facing areas will get a lot of trees that can grow with less solar energy. And then the water, the soil moisture stays there longer, promoting more growth. And so this creates extreme challenges to model snow and the heterogeneity of watershed SWE. And so getting to the modeling workflow, a lot of my modeling work started with the Snowcast Showdown. So this is a program by the U.S. Bureau of Reclamation, NASA, NCAR, that's the National Center of Atmospheric Research, USGS, USDA, on trying to improve representation of snow to help with streamflow forecasting. So our first model was a bunch of different machine learning models. And so we used a deep neural network to have 23 different regions. And so our logic behind that was that snowfall is different in coastal Oregon, the Cascades, the Southern Sierras, as it does in Colorado, and then in the Northwest area, like in Montana. We had a training period that was provided from 2013 to 2018, and we wanted to kind of develop that serial correlation in snow accumulation and melt. Modeled at a 1 kilometer spatial resolution, which is, in the snow modeling world, it's kind of about standard for operations, and it's going to be on the very high resolution theme for a lot of these climate models that are doing, a certain amount of degrees. And we came up with a snow modeling workflow. So we trained our model on those airborne snow observatory observations. We used in situ observations from SNOWTEL. We had a DEM, so a digital elevation model of the terrain. And then we used some the NASA VERS imagery. So basically, we used a fraction of snow-covered area. So was that area covered by snow, or was that area not covered by snow? We developed a data processing and feature engineering workflow. So that's where we kind of had those features that related to serial correlation of snow melt. So basically, yesterday's snowpack is a direct driver of what today's snowpack is going to be. We assimilated and processed all these spatial observations, and we trained them in a gradient boosted decision tree model. That helped with our feature selection of what features are going to be the strongest drivers and to inform our machine learning workflow. We optimized these features, and then we trained several machine learning algorithms. We trained XGBoost, like gradient machine models, regression models, deep neural networks. And while we were training this model, we're making predictions at the same time. And this was for water year 2019. And we actually had a really long snow drought. And so snow droughts, we have no precipitation for a prolonged period of time. I believe it was from like January 15th to mid-March. We had no snow. And it made it for a very easy decision of what algorithm to select. And it ended up being a deep neural network. All the tree-based algorithms were showing an increase in snowpack with no snow. And so that was a pretty easy identifier of why we went with a deep neural network. And then from this, we ran a bunch of different simulations. And so here we have a simulation of 2019. We could compare it to a lot of the what the observations were for that entire year. And it just really helps us to understand the strengths and weaknesses of the model. So we see really good prediction skill with our modeling workflow in predicting the mean catchment snow water equivalent. So basically our blue value or our colored value in here, depending on the type of snow classification, is very close to the black line, which is what was observed in that catchment. The challenge was we didn't see for every catchment capturing the variability of that snow distribution. So the gray line, kind of background area, is what was observed for the kind of the maximum and minimum snow within a certain catchment. And so for some catchments, you did really well, like the Sawtooth, so in Idaho, we did quite well. Southwest Montana, we did pretty well. We did well in the Northwest Rockies, the Northern Wasatch. But many areas, we did not capture that strong variability in snow. So the upper Colorado, so this is by like kind of close to Denver area on the other side of the Continental Divide. We're not capturing, the low or the high amount of snow distribution. And we see a similar problem within the Sierra Nevada mountains. The Great Basin, we were good for the first part up to Peak Sui. I didn't capture it for the second part. So these are all kind of drivers of how we want to improve our predictions. And so a key item, we saw some significant limitations with that regional model design. We weren't going to be able to do good predictions if we didn't have good in situ observations nearby. And so we kind of wanted to solve that. We want to be able to predict any location in the Western US with some, a certain level of confidence and accuracy. And then some new themes within the machine learning world is you want to have a better machine learning model. And the best machine learning models tend to have from exploiting all the information that's available. So this is some great work by Kradrix et al. And what they're doing is this is they kind of been adapted from streamflow modeling, where they're training a model on all the different catchment information that they have of various different catchments, rather than just on a certain catchment of interest. And what this helps do is you have maybe arid catchments or arid snow environments, and then you have wet snow environments. And then operating under that assumption that a model will be able to take information from that arid snow environment to help predict maybe a very low snow year and a traditionally wet snow environment. And then vice versa, if we have a very wet snow year and a traditionally dry snow environment. So trying to exploit the power of machine learning and translating conditions from different regions. We want to leverage more spatial data. We weren't able to use all of our spatial information in our first machine learning version model, just due to data processing limitations. So we want to make sure we could use all the spatial information that was available to us. We previously modeled at just 1 kilometer spatial resolution. A lot of snow processes happen at significantly smaller spatial resolutions. So we wanted to have end user flexibility in modeling different resolutions. So we started at 50-meter resolution, and it can go anywhere up from that. 50-meter resolution is going to be what our NASA ASO data is provided at. We want to have an expedited data processing and training routine. So we just want something to be very quick and mobile. And so if we want to add a new feature into our machine learning workflow, it's quick and easy to do. We want to have everything be modularized so they can have just very simple plug and play design of how to add features, take features out. And then with that overall motivation is we want to capture that spatial heterogeneity of catchment snow distribution. So basically, we want to have the whole catchment distribution. We want to fill in all these gray areas with green. We want to have a stronger implementation of precipitation. Our previous model was just spatially extrapolating information across the terrain from the different point observations. We want to have precipitation products help drive our machine learning workflow. We saw how important energy is, and energy drivers are from energy on snowpack. So we want to have some energy components or be able to put them into our workflow. And then we want to have a mass balance. So previously we did pretty well at this with that zero correlation, but we're going to look at into the future having some kind of mass balance components built into our machine learning workflow. All right, so let's just go over some study areas. So we focused on these airborne snow observatory regions, and that's going to be used as our module target for predicting snow water equivalent. And so we have several catchments in the Sierra Nevada mountains. So we have, the San Francisco area right here, directly east of them. We're gonna have like the Tuolumne, Merced, San Joaquin, and Kings River basins. We have the Colorado Rockies. And so we have the East Taylor, the river, Upper Rio Grande, Conejos, and the Blue River Basin. So like the Blue River Basin is up here. We got Denver right over here in this area. We're going to have the Taylor River Basin. So this is where Crested Butte, Colorado is, and part of the headwaters of the Gunnison River. We have the Upper Rio Grande right in this area, and that flows south out of Colorado. And then we have the Conejos River Basin, that southern part right there. And then we also want to have, we're going to expand our data to the Pacific Northwest. There's a couple of flights in the Olympic Peninsula. And so we want to use that diversity of information to help train our machine learning models. So we want to have different features put into the machine learning workflow. And we're kind of seeing these different snow environments. So a lot of that was captured by that regionalization in our previous workflow. Well, we thought we could have some features built into our model to help differentiate between these different snow environments. And so the Sturm snow classification is a product that classifies many different regions by grid cells throughout the Western US for these different environments. So we have tundra, boreal forest, maritime environments, ephemeral, so snow that may stick for only a short period of time, a prairie environment, so kind of high elevation, where it's cold and snow may stick for a little bit longer. It doesn't develop a deep snowpack. And then a lot of the montane forests where snow can remain somewhat protected from the sun under the canopy. And so we have this for Colorado. And we also have it for kind of the in the Sierra Nevada region. So we have this feature for all of the locations is put into our modeling workflow. We want to have a precipitation product. So we first started with the National Land Data Assimilation System. And so we do seasonally accumulated precipitation to wherever our training data points of interest are. And so we can bring in observations from the Sierra Nevada, Colorado Rockies, and this is a very standardized and validated precipitation data product. And you'll see that it does have some potential errors that we identify later in the presentation. We're going to have vegetation within our component. We saw how vegetation was different on our previous images. So we're using the National Land Cover Database. We're using the NASA Visible Infrared Radiometry Suite, and that's a normalized snow difference index. And that helps us to, with fraction of snow covered area. Is there snow at this point, or is there not snow at this point? We use our 30-meter digital elevation model. So we're getting elevation, slope, and aspect from that. We're using in situ observations to help that spatial extrapolation process. And so we have current snow water equivalent, historical, daily means. So we can develop some ratios of the historical means. Oh, is it a big snow year? We have a lot of more greater than average. Is it lower than average? Then we're putting in some seasonality components. So we have into our machine learning workflow, we have in situ observations. And so that's going to help inform us, how much snow are we having at this point in the year? How does that compare to historical amounts of snow for that region? And a key component of what enabled this one model workflow was using the Haversing distance formulation. So what this is doing is for any point of interest. So if we want to choose a location here, we're actually grabbing the nearest observations. So for this point, maybe right here, we're grabbing the nearest in situ observations from A, B, C, D, etc. We're using that Copernicus DEM, that NASA imagery as we did previously. And then we're adding these new products with precipitation, vegetation, and then that snow classification. We rebuilt our data processing feature engineering workflow to be modular. And then for what we'll see here is we're doing a target of a 300 meter spatial resolution NASA ASO observations. And we've trained our machine learning algorithms. We've played with some feature selection, and we've assessed algorithm performance, optimized our hyperparameters. And we've led to, currently back to using an XGBoost algorithm as an optimal algorithm for the spatial, basically that snow mapping product. So how did we train our model? And this is what is very important with a lot of machine learning work. And a lot of this is still preliminary, so it's going to evolve over time. But we felt it was extremely important to do a hold one out model approach. And so what we're doing here is we're training the model, hold a location out, so the model has never seen a certain location, at least during the certain water year, and then making a prediction on that. We're using ASO images from 2013 to 2019. We're removing bad scenes. So there's some scenes that have just extreme outliers that are like 5 meters of snow water equivalent, which is unrealistic. A lot of images have just zero snow water equivalent for our entire basins. This led to 97 scenes from the Sierra Nevada, 11 scenes from the Colorado Rockies, and then 2 scenes from the Olympic region. We removed values of less than 1 centimeter of SWE. So that's why you see in some of these images to the right, or basically the ASO target, there's these kind of cutouts, and that's just there's no snow or it's very little snow in that area, and we're not really focusing on modeling that. At that 300-meter spatial resolution, we have 800,000 data points to train our machine learning models on, which to me is quite high. So let's look at some of the results. We'll try to wrap this up. Looks like we're getting close to our time. And for the Tuolumne River Basin, so this supports Hetch Hetchy Reservoir and San Francisco area. There is a lot of flights, those ASO flights in this region. And what that's done is there's a lot of training data for this model. So we see quite high model skill with a KGE 1.85, pretty low percent bias, and 11.6 centimeters for RMSE, pretty low. We can look at how much, with the different elevation bands, how close are we to what the observed PSW is. And so you see we're pretty close within all the different elevations. And then, the real item we're concerned about is how much water is at these different elevation bands. And we see that mid elevation band has the most area and is the most important for water supply within our catchment. And for all the different elevation zones, we're very good as far as how much water we're estimating. Within our images, we have the ASO images right here. This is our truth. And then we have the error. So where is the error in our model? And so within here, blue is over prediction, and then red is under prediction. And so we're under predicting some along this ridge, some of this area over here, and with strong over prediction kind of on this western flank of our catchment. And then we want to see where is that error potentially coming from. And when we look at our precipitation product, we're getting or showing the highest amount of precipitation on this western front. So where we see the biggest error, our precipitation product is showing the greatest amount of precipitation. And then similarly, where our precipitation product is showing the least amount of precipitation, we're showing we're under predicting in those areas. And then a lot of this, look based on our orographic precipitation figure we saw earlier, there's a lot of, I'm not sure our precipitation product is the ideal product we're using right here. I would expect to have higher precipitation at the higher elevations, close to this crest, definitely not the lowest precipitation. Look at just another basin in the Taylor River Basin, Colorado. So this is the Upper Gunnison area next to Crest Butte Ski Resort. And we see a similar relationship to our Sierra Nevada location. We happen to be over predicting snow in this basin. So we'd be overestimating how much water is stored as snow. And a lot of this is due to an over prediction kind of this northern high elevation component. And similar to our Sierras, we are over predicting our snow where there is a high amount of precipitation right in this area. I don't know, this precipitation could be correct. Higher elevations tend to have more precipitation, but also I'm not sure if we should be seeing lower precipitation at these high elevations in the south and eastern parts of our river basin. And then a very important part of evaluating machine learning models is how does the model perform in a location that has never seen. So the Conejos River Basin is a river basin that is not in any of our training data. So we are making a prediction on a basin that model has never seen. So this is what we could expect the model to perform in basins that aren't within that ASO training data set. And what we see in this is we are severely under predicting the snow on the ridge. We are over predicting or under predicting the snow that is happening below that ridge line, and then over predicting snow kind of at these lower elevations. And when I look at this, I see we are over predicting and then under predicting right along that ridge line. That's probably from wind transport. So you see a lot of wind coming from this area from the south and from the west. And so these kind of give ideas of how can we improve our model workflow. And then once again, we do see over predictions happening where we have higher levels of precipitation from our precipitation data product. So these kind of building this story that we need to have some wind redistribution features and that we need a better precipitation product to help drive our models. And then lastly, a component of evaluation, we want to see how our model is doing compared to current operational products. And so SNODAS, the Snow Data Assimilation System, is a physically based snow model with some assimilation components that is operational, and it's used by many different government entities. And then here we have our model put within what's called the National Water Model Hydrofabric. So each of these little polygons is essentially a catchment. And we aggregated the snow in each catchment and then compared it to the observed, which is that ASO data. And so we see like we have some pretty high model scores. It's a little bit off from the SNODAS component, which has had years of evolution. And so to us, it looks like for our first or second generation machine learning modeling product, we're going into the right direction. All right, so we built our model. So we know snow is important. We know it relates to stream flow. We built our machine learning model. We just evaluated it. So what leads to those next steps? So it's important to have some reflection, assessing the model performances. And so we saw from our feature importance, which is a very useful tool generated by any kind of decision tree model, that precipitation is the most important feature. And they see seasonality, so that's the DOS, the day of season, and WY week, water year week, are important drivers. So that's seasonality, which we would expect. The snow classification Stern value is important, so it's helped differentiating the different regions. And then our nearest sites, which are these NS values, are all strong features within our modeling workflow. We also have elevation in there, which we would expect as well. Some unexpected results from our feature importance figure, our aspect and slope are not substantial components of our model's decision pathway. And so what are the steps? What are we going to be doing next to help refine our model? So we got to select where it performs well. So it performs well in locations with multiple ASO flights. So let's have that first figure from the Tuolumne River Basin. We're seeing that's challenged in locations that has never received any kind of training. So in the Conejos Basin, we're seeing some issues with precipitation forcings. It seems to be responsible for the greatest error, but it's also the most important feature within our model. We're doing some high resolution snow mapping. So we're demonstrating at 300 meters. What if we redid our maps at 1,000 meters? We did it at 750, 500. How is that going to influence our model performance? And then a benefit is, we're doing 100% open source. So everything's model agnostic. There's a GitHub link at the end here. And you can do all the data processing and training on a laptop. So it creates a nice avenue for future development. So steps to advance these capabilities, we want to include ASO Inc. spatial data products. We included NASA ASO data products, which is only from 2013 to 2019. And so the ASO Inc. goes from 2020 up into 2024. So we'll have more data to train our models. We want to include some snow survey observations. So we don't have any in situ rural observations that we're training against. We use the in situ monitoring stations as model inputs. And so some of those observations, the Citizen Science Snow Observatory, and so there's a lot of information there that we could use. And there's also snow exmissions. We'd also like to model snow depth as a target, in addition to snow water equivalent. And then we want to assess different precipitation products. So we have like the Prism product comes to mind. That's also at a higher spatial resolution. We're looking at about 800 meters versus 12 kilometers. Also the analysis of record for calibration, AORC, that's an 800 to 1 kilometer data product. And then the NOAA high resolution rapid refresh, which is used for operational forecasting. And that's at 3 square kilometers. We want to do some precipitation phase determination. So is the precipitation following as snow or rain? So we want to do that based on wet bulb temperature or explore wet bulb versus just temperature. Being in Utah, it'll snow at 45 degrees sometimes. So we need to make sure we're including what the snow condition is or how it's falling. I'm going to do terrain and wind. So we want to have better spatial terrain relationships. So think about if we're looking at from like a vertically above the terrain, like wind shadowing, what are the regional features that might affect snow for a certain area? We also want to include that wind redistribution within our modeling workflow. Then we want to have some energy components. So we want that shortwave energy, long wave, and that relationship for the time of year and incoming radiation. We're looking at algorithm optimization. So right now we're just using XGBoost. We want to use LSTM, some deep neural networks, CNN to get that spatial relationships, maybe even some Gaussian-based machine learning modeling workflow. We want to have some physics-informed learning. And so we want to put some physical constraints in our model. We're going to be putting some mass balance components based on that serial correlation and have some energy balance methods within the modeling workflow. And then we're going to be assessing different spatial resolutions, so different grid scale resolutions, mesh optimization, and then kind of we saw those polygons, put it in that hydrofabric for that spatial discretization. And so we also want to demonstrate capabilities of snow to flow. And so we'll be deploying our model, working on some of the Utah resources, so it's semi-operationally. And that allows NOAA allows us to see how the model operate in an operational environment. And I'll be coupling it to some streamflow models. So we have a national water model post-processing machine learning workflow that has a snow component. And so we want to see how refined characterization of snowpack influences the model. And that'll help us identify some snow response units and demonstrate how the snow modeling skill can improve streamflow and water management operations. And with that, I'd like to really thank my collaborators. My previous advisor, Dr. Stephen Burian, was very supportive of a lot of this exploratory research. My colleague, Ethan Ritchie, who is a master's student at Colorado School of Mines. Has been very influential and helped designing some of the evaluation framework. My colleague Andy Wood helped design that evaluation framework. And then my current grad student and partner in developing this project, Dan Liddestrand, has been instrumental in help with all the Python code and making this project work. And with that, that QR code will take you to the GitHub repository if you'd like to, either fork it or be a contributor or just want to learn more about it. And I'm happy to take any questions if I have any time left. Guess I'll look to you, Sangming, for any kind of information there.
Thank you, Dr. Johnson. It's really, really great presentations. Wow. So it
Thank
was
you.
really, yeah, really good chance for me to learn the many things related to the like snow, water, and it's really interesting. And then how to apply the machine learning model or data-driven models for water resources management based on the snow and the water relationship. It's very interesting. I think there would be a lot of some questions, I think, because many students and also my colleagues have very interested in this presentation, I think. So I think in the chat meeting chat, we can see some questions. So the first question is data simulation is a crucial task while modeling using machine learning. The how is it handled while running the simultaneous models together? And is it the series computing approach and parallel computing? So maybe you can answer this question.
Yeah. We'll try to make our way through these. I don't have like
Yeah,
a dead hard stop, so I can stay a little longer if you want to answer some of the
yeah,
questions.
yeah.
So as far as data assimilation goes, we're using all these in situ observations from the SNOTEL sites. And so part of our, on the current modeling workflow, I have not set it up to work operationally yet. Our previous workflow, so I demonstrated our snow water equivalent machine learning version 2 that built off those limitations of version 1. Version 1 is running semi-operationally on the University of Alabama high-performance computer. And the assimilation process is essentially the same. It is parallel computing, and it goes and grabs, every time we make a prediction, it'll go grab the most up-to-date snow water equivalent value from all of the SNOTEL monitoring stations. And so that's been revised over the past couple years just to make it more efficient. We used to go to California, always has to be, throw a wrench in the gears. And the way we access their data has always been different. And they like to change their URLs often. And so that has been a challenge for us. But we've been working with Quasi to develop a more robust data collection system. And so we have all the scripts are within that GitHub. Every component of our data processing workflow could be used for getting near real time data, and it's very modular. So someone interested in, maybe they don't care about the remote sensing products, but they want to go and I want to get the snow data. I want to have an easy to use script so I can get snow for my project. It's in the get in situ snow observations Python script, which is only a couple, 200 or 300 lines of code. So it's pretty easy to go in there. There's functions that someone can just go in there and clip out and use for another project of interest. And that's all when it's operationally. It just runs through those different scripts and executes. We grab all 1,000 SNOTEL sites, current SWE value at the same time. And I think it takes like less than 30 seconds to go grab all that data.
Okay, and then the second question is, do you use only the pre-developed machine learning models, or do you incorporate some new algorithms or new things into the existing algorithms?
Yeah, no, that's a great question. Right now, we're just using kind of off-the-shelf machine learning products. So I like PyTorch. So PyTorch has been really good. I haven't, I am not a computer scientist. My research group is not computer scientists. So I haven't seen a need, or maybe we don't have the capabilities to go and, develop a new neural network algorithm. We will be exploring different loss functions, which PyTorch allows you to do. So for right now, we're just using off-the-shelf the algorithm. The hard part about machine learning, or the emphasis that I place on it, is in the data processing, getting the right features generated, and then having a rigorous evaluation.
Mhm.
And so until I feel like we've optimized or like brought those to the highest level, I don't see a need for us to go in and start making our own machine learning algorithm.
That's cool. I, okay. So next questions. Can you share some insight on the seasonal trend? There's a snow decompositions in the prediction model. Yeah.
Yeah, I mean, as a seasonal. So what we're doing right there, so we have a couple like simple metrics, and this is an area where we're going to be growing. I'll explain in a second. The seasonal trends, like there's a strong relationship between like the time of year and snow. And so like we have generally like beginning of the year, October, we're not going to have that much snow. And so we simple features, there's like how many days from the beginning of the water year are we? And so we had the DOS, so day of season. That starts October 1st and it just increases until it hits 365. And so that was a strong feature in our machine learning model. So it's generally like we have that October or that April 1st point should be around that peak sweep point. And so that's around like I think day 200 or something. And that's a strong indicator or a strong seasonal driver or seasonal feature for snow water equivalent. And we also have water year week. And so that's kind of, it's just more of a lower temporal resolution metric. We also have seasonal metrics built off of our observations from our snowtail sites. And so that's, we have what the what the median SWE is at a certain site, and then compare it to what the current is. So I have this for the certain point in the season, are we above or below for that location? As far as in the future, I want to have more of the solar energy seasonality. So what's like the solar zenith angle? How does that change throughout the year? We don't have high resolution, or I don't think we have high enough resolution energy shortwave radiation products out there, but we know the sun's not, hopefully the sun's not moving as far as like in its orientation for this time of the year. And so we have an idea of how much energy is coming from the sun throughout the year, and we relate that to maybe like the slope angle of the terrain. So we can have, a more characterized how much energy is hitting that particular grid or area of snow. So that'll be kind of the area for future research my grad students are working on.
So while I was in the Utah state, I never seen something kind of flood issues before. So is there any the flood records due to like the snow melt in the April, the summer in the Utah state?
So that we were very concerned about it 2 years ago and last year with our record-breaking snowpack. We had
Uh-huh.
like Alta I showed had 900 inches. That's over 100 inches more snow than has ever been recorded. Keyword
Oh.
recorded. And so we were worried about flooding. We had a very slow snow melt that year, so a gradual warming. So it wasn't like a rapid snow melt event, and so rivers sustained a high, gauge height, but nothing wouldn't lead to any flooding. There has been flooding in the City Creek area from City Creek, historically, and so that's people where we can see there's pictures of people taking their canoes and kayaks down the middle of Salt Lake City when the
Uh-huh.
stream overflowed. So that I would say that probably not a history of flooding here in Utah, but I think 2 or 3 years ago, there was huge Yellowstone floods. So there was a
Oh.
massive snowpack up in Yellowstone, and then there was a long rain on snow event. So I think it was probably May or April or May or June. And so you had warm weather and precip or a liquid precip falling. And
Mhm.
so that rain on snow event, like it took out tons of roads up in Yellowstone National Park, caused a lot of damage, and it was largely unpredicted. So we didn't know how much snow really was up there. And like I looked at the national water predictions that captured none of the gauge height. Like the river was flooding so high, it took out the bridges that hold the gauges. And
Mhm.
so like these kind of events, I think are going to be more common in the future. We're going to see, how the climate goes in the future is uncertain, but there's potential for bigger snowpacks at high elevations and then rapid melt. And
Mhm.
so those situations may become more common. And so we need to better characterize where the snow is rather than just a point observation, rather than the current kind of lump modeling approaches of a lot of what our river forecasting centers use with their 60-year-old Sacramento soil moisture accounting models, which work well, but they're not going to capture that spatial heterogeneity of snow in these catchments.
That's great. Thank you. I think we have the last question. I think what strategies can be implemented to improve the performance of the model and the catchment with no prior the training data, and how can the accuracy of precipitation forcing forecasting be enhanced to reduce the errors despite their importance in the model?
Yeah, so I think the biggest thing is putting more physics in the model. Which, you know, if we're putting the physics based on the precipitation forcings we're using, there's going to be some remain error right there. And so that's why I think the first effort we're going to be doing is focusing on look at different precipitation products. Very curious with what Prism can do with the analysis of record for calibration. So that's our first component into reducing our error. And once we have I think a better precipitation product, work on implementing some of the physics. So physics will help in those regions that have, you know, the model has not seen, so it doesn't have like a kind of a base or foundation to build off of, and it'll put snow in the correct places based on maybe the physical processes rather than, you know, seeing so many images of the same catchment over and over again.
Okay. I was also curious because when I look at your result, the RMSE, the 9.57 centimeter, like the 18.5, I'm just wondering that those kind of those so this is acceptable errors, or how is the performance of the model based on this RMSE?
So that's why we use more than one metric.
Yeah.
I think our where the worst error was had the least RMSE. And so that's yeah, and so
So our
it's
square also like a 0.5 or 0.45. So I just was wondering this is okay or not. What is the good numbers for the reliable model performance? That was my
it's
question.
really, if we look at RMSE, it's going to depend on catchments.
Uh-huh.
So the reason like RMSE, you know, like that 9.5 centimeters, which to me is pretty good. I think anything under 10 centimeters is pretty good.
Uh-huh.
But you got to relate it to what the other areas are. So we don't have that the Conejos catchment is in southern Colorado. They don't get as much snow as like the Sierras. So that percentage of that air compared to how much snow falls is quite higher than even though we were had a little bit higher RMSE in the Tuolumne River Basin.
Mhm.
So we we want to look at that percent bias. You know, are we over? You know, how are we over predicting, under predicting? I like using the KGE value. That's kind of like my first attempt golden standard as to how our model is doing. But I see a lot of modelers, but especially in the machine learning world, that are purely looking at just these metrics to say, oh, I have a good model. And so a lot of my emphasis and projects I'm working on right now is to more rigorously evaluate models. So that's why we're looking at locations the model has never seen. We are looking at the spatial error. So I show different elevation bands. So I want to evaluate how, you know, really look in more in depth at how our model is performing on those parity plots, the different elevation bands, look at the different aspects. So how's the model, you know, does aspect and influence? And that's going to really help us identify the weaknesses in our model so we can develop features or processes to improve in those certain areas.
Okay, thank you, thank you for the answers. But I think we have more questions. So, do you have a time, or I think it's
I have a
already
few more minutes. I gotta get up and give the same talk up at Utah State in person.
yeah. So I think the last question would be how can we evaluate remotely Glasgow coma scale using the machine learning? So
Let's see, let me do it quick. I have not used it yet, so let me just get a quick background. Um, let's see. I don't have, I guess, an answer for that right now.
oh yeah, it's okay. I think. uh, yeah,
I
I
just see
think
one like a time range, maybe for observation data sets. Let's see. Any specific reason?
selection time range for observation data set. Yeah.
So yeah, I can kind of touch on that. So the time range, we're just taking all the data that we have. and we are data limited. So a lot of those spatial data sets, like, they're expensive to fly. So they're not taking a lot of flights early season. So we are going to struggle with doing early season snow because the model has no idea. It's never seen any early season snow. We'll be most accurate around kind of that probably late February to mid-April or early May timeframe. That tends to be when we have the most images. And then we'll also could struggle with some melt. So we'll be able to correctly predict where snow isn't, but where snow is has some opportunity for limitations. So we want more data. And so part of my other research is doing snow instrumentation and spatially distributing throughout watersheds. So we can kind of collect nonstop seasonal data so we can improve snow accumulation and snow melt, especially snow melt out or like that 50% of the snowpack being melt. So that's why we're using that time range. I would put, if we had data from every single day, which there are some opportunities for that I believe, we're going to pursue those.
Okay. Okay, thank you, Dr. Johnson, for all the answers in your presentation today. I think we have to stop the webinar today now. We really appreciate your times. Dr. Tiwari, so do you have any things to announce for the next webinar or finalizing the webinar?
Yeah. Am I audible?
Yeah.
Oh, perfect. Thanks, Dr. Ryan, for giving such a nice presentation. I'm really admire it. You took uh, I have never seen a presentation like this where the speakers are even explaining a small data set, how they prepared that data set, and so it's extremely useful presentation for developing a research actually. So somehow the limitation whenever I attend any webinar, we get what they did and we can never implement it again. But the way you presented the thorough methodology and like how the students or even the researcher faculty members can extend that research using your open source code and GitHub, I really admire it. Recently I personally started working on these kind of data sets and everything, so I'm going to use it for sure because I'm working on like a debris flow on a fire hazard area where wildfire hazard happened, and I think the snow melt can be one of the potential source to trigger the like earlier we were thinking to do only the rainfall, but snow melt is one of the major reason, and I think in LA we already observe a lot of snow melt. So I think that is going to be one of a very interesting area for me to explore personally. So thank you so much for a nice presentation. I really admire your time. Dr. Himali, do you mind to announce the next webinar, and then I'll announce the another following webinar? You are mute.
Again, thank you, Dr. Ryan, for your very clear and presentation. I really enjoyed it. I have little background in rainfall runoff modeling, and so this was really interesting to get to know about the snow prediction and modeling. So it was very interesting. So for the next presentation, we will have Dr. Yaling Lee, an assistant professor from the Rutgers University. So we will share the meeting invite and link pretty soon. Okay. Yeah.
And following to the next this presentation which Dr. Himalayan announced, we have another presentation coming from UC Davis, Mr. Dr. Nikhil, and he is going to present the effect of the wind. So like a wind hazard. So like we covered rainfall, we covered snow this time, and in the future we are going to cover the wind effects also. So let's get in touch, be in touch with us, and we are going to email you soon the next webinar. And this is going to be one of the very nice series. We are going to post this complete webinar on YouTube so that people can rewatch it, revisit it, and they can explore the research. And I'm sure Dr. Ryan will be happy to answer your questions if you have any. Thank you so much for joining our webinar today. Thank you.
Thanks, Ryan, and thanks also everybody.